to today's Friday Math Happy Hour. Today we're going to cover the exam 2 review, which more than likely is going to be next week. Okay, because if we would have covered it next Friday, it would have been a little bit too late for some of you guys. So this semester we're going to do them the Friday before the exam week for the exam 2 week. Okay, the topics that I'm going to cover are chapters 4 and chapters 5. Okay, so let's start with the first topic, which is 4.1, which is graphing exponential functions. So, for example, number 1, graph f of x equals 2 to the power of x. So the best points to use, values for x are, always between -2 and say 2, or from -2 to 3. So in this case, we're going to do from -2 to 3. Okay, so let's draw a little table. Right, so these are the values for x. Let's start with -2. When x is -2, right, we're going to go here to the function on the right. We're going to plug in -2, for the x. So it's going to give us equals to 1 over 2 to the second power, which will give us 1/4. So when x is 2, y, or f of x is 1/4. We repeat the process until we get all the way to 3. Okay, so let's continue with the process. So when x is -1, y will be 1/2. When x is 0, 2 to the 0 will give us 1. So y is 1. When x is 1, y is 2. And when x is 2, 2 squared will give us 4. So y is 4. And finally, when x is 3, 2 to the third power will give us 8. So y is equal to 8. Now we just graph our graph. The graph will be this one here on the middle. Okay? For example, when it's -2, right, if you notice, this is 1 for the y value, so at -2 is about 1/4. At -1, it's about 1/2. When x is 0, y is 1. When x is 1, it's about 2. When x is 2, we go all the way to 4. And when x is 3, we go all the way to 8. Because that's why we don't choose numbers that are real big, because if we choose 4, right, 2 to the 4th power will give us 16, and 16 will be way out here. It'll be out of the grid. That's why these are the x values that we recommend for you guys to use, like from -2 to 2 or from -2 to 3. Okay. Okay, now number 2. Let's graph f of x equals 2 to the power of x minus 1. Again, we're going to choose the same values. Okay, but now we're going to go all the way to 4, because 4 minus 1 will give us a 3. Okay, so here we go. When it's -2, it's going to be 2 to a -2 minus 1 will give us 2 to the -1/3 to the -3rd power, which will give us 1 over 2 to the 3rd power, which will give us 1/8. So when x is -2, y is 1/8. When x is -1, right, we're going to plug in -1 for the x. So -1 minus 1 will give us -2. 2 to the -2. 2 to the -2 simplifies to 1 over 2 to the second power, which will give us 1/4. When it's 0, right, 0 minus 1 is -1. 2 to a -1 will give us 1/2. So when x is 0, y is 1/2. When x is 1, right, 1 minus 1 will give us 2 to the 0. 2 to the 0 power will give us 1. So when x is 1, y is 1. When x is 2, 2 minus 1 will give us 1. So 2 to the first power will give us 2. So when x is 2, y is 2. Let's try 3 now. When x is 3, 3 minus 1 will give us 2. So 2 to the second power will give us 4. So when x is 3, y is 4. And finally, let's use 4. So 2 to the 4 minus 1 power will give us 2 to the 3rd power. 2 to the 3rd power will give us 8. So when x is 4, y is 8. Let me go back here. y is 8. So this is a graph. Well, let me go back real quick. I think I didn't graph this one. Hey guys, but the graph for this one would just be this graph. Every point moves to the right 1 unit. I mean horizontal, because this is horizontal shift. And I apologize for that. I didn't graph the graph here. But every point, if you notice, from the original one, every point moves to the right 1 unit. So for example, when it's this is 0, 1, so that's going to be 1, 1. You see, there it is. And I repeat, this is horizontal shift. Okay. Okay, now let's go on to the exponential graphs. So let's graph d of x equals 2 to the negative x. So negative x is going to give us, right? So we use the properties, which will give us g to the negative x is the same thing as 1/2 x. So this is the one we're going to be graphing. Okay. And like before, and we plug in -3 here, right? And we plug in -3. It's going to give us, right? We use a reciprocal. Remember from the rules I did, I believe, about 2 weeks ago? So we use a reciprocal and it becomes positive. So it's going to be 8. Right? And we continue the process all the way through. Okay, for all these right here, from -2 to 3. Right, so we continue the process. When it's -2, it's going to be 4. When it's -1, when x is -1, it's going to give us 2 and so forth. So anyway, this is the graph. At -3, right, it goes all the way to 8. At -2, it'll give us 4. At -1, it's going to give us 2. At 0, it's going to give us 1. At 1, it will be 1/2. At 2, it'll be 1/4. And at 3 is going to be 1/8 is real close to the x-axis. That's the reason why we don't use numbers more than 3, because all these numbers, as the graph goes to the right, positive, the graph will get closer and closer and closer to the x-axis, but it will never reach it. Okay, so that's why it's useless plugging in 4, 5, 6, and so forth, because the graph will eventually, like as repeat, it will get closer to the x-axis. Okay, now number 4. It says the assets in billions of dollars for the Prudential Financial Incorporated can be approximated by the function a of x equals to 315 e to the power of 0.056x, where x equals 7 corresponds to the year 2007. Find the assets for the following years, the year 2000 and the year 2012. Okay, now this is my solution. Okay, this is what we're going to do. Since x corresponds to the year 2007, then x equals 0 must correspond to the year 2000. And for 2012, x equals 12 will correspond to the year 2012. So for a part, I'm going to evaluate a of 0, which means I'm going to plug in 0 for every x. You see in green. So e to the 0.056 times 0 will give us 0, right? So e to the 0 will give us 1. And 1 times 315 will give us 315. So this will be 315 billion because the assets are in billions of dollars. Now for B part, okay, one more thing, guys. This is good to know. 315 is the initial value because time is 0. When time is 0, the initial value will always be the coefficient that's here in front of e or in front of the exponential power here. Okay, that's good to know for the next problem that we're going to be doing. I think problem number 5. But let's continue with B. So for B, we're going to evaluate a of 12. That means we're going to plug in 12 for the x here. So here, we can just put in the calculator, right? And make sure that that the exponents are both together in parentheses. That way, it makes sure that it gives you the correct answer. This is my answer. So they round off to the nearest 10, right? But remember that the answer is in billions of dollars, so that's why it's going to be $616.8 billion. Okay, now let's move on to number 5. Number 5 says a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. This is like 2 parts. The first part is find the model of the form f of t equals to y naught b to the t, with t equals 0 corresponds to the end of the month of January. Then for part B, if the trend continues, about how many people will be infected by the end of the year. Because remember, guys, that I told you when t equals 0, right? This coefficient here is my initial value. So in this case, we need to find y naught and b, right, to plug into the formula. Remember I said y naught is the amount present at when time equals 0. So before any, so let's get 2 points here. T equals 0 corresponds to the end of January. That means there were 128 people infected. I know there were, let's see here, there were 2 cases, and then by the end of the April, cases had grown to 128. So the 2 here, guys, on top is my y naught. Now t equals 1, right, corresponds to February, t equals 2 corresponds to March, and t equals 3 corresponds to April. That's why I'm doing this, so you guys can, this will be more visual. Because it's saying here, by the end of April, the cases had grown to 128. So from t equals 0 to t equals 3, right, 3 years passed. Which was, not 3 years, 3 months passed, and there was a total of 128 cases. So we can go from t equals 0 to t equals 3, which will be 3. Right, so use what we know to find b, because we already know what the y naught is, or the initial value is 2. Right, so now we're starting b. So f of 3 equals 128, which means 128 equals to 2, right, my initial value, b to the 3rd power, because f of 3 is we plug it in for the t here. Now in this problem here, all we do is solve for b. So the first thing we should do is divide by 2. If we do that, it's going to give us 64 equals b to the 3rd power. Now we raise each power to the 1/3 power to get rid of the exponent here. That way we can isolate the b. Right, so we do that to both sides. So here, 64 to the 1/3 power will give us 4. That means my b is equal to 4. So I already have my y naught, which is 2, and my b. So now this will be the solution for A part. F of t equals to y naught b to the t power. We plug in the values. My y naught is 2, and my b is 4. So this is my function for part A. Okay. Now from January to December will be 11 months. Right, so for B part, I need to find f of 11, which means I'm going to plug in 11 for the t here, right? Because this is f of t, so that means we're going to plug in 11 where the t is in the formula right here. We use the calculator, so this is my solution, guys, right? So about 8,388,608 people will be infected by the end of the year. I use an example when we were dealing with COVID. I believe exam 2 was right before spring break, and after spring break, that's when other classes went to their transition to online. So I was trying to use the example, like in the real world, right? The example about COVID, how we can apply mathematics to find about how many people will be infected, approximately in a certain amount of months or a certain amount of days. And that's how we use math by using the exponential function. But here, guys, since there was this means if there's no intervention, right? But there was intervention during COVID. For example, there was social distance, there were masks. So with the social distance, it wasn't that many people infected here in the United States. But I believe in the world, it was more accurate. Yeah, it was more than 8 billion, I think. Throughout the world, because a lot of people were getting infected. But anyway, this is how you use math in the real world. Okay, now the next topic we're going to cover is solving exponential equations. So this is like the property or the rule that they have. Let a be a positive real number with a cannot equal to 1. So here's my condition. If a to the u power equals to a to the v power, then the u must equal to the v. Okay, example. So you have 3 to the x power equals to 3 to the fifth power. You see, guys, the a is called the base. So if you have the same basis, you can apply the rule. Okay. So for example, here, right, we let the exponents equal to each other, so x will equal to 5. Number 6. If you notice, the bases are 125 and 5. Not the same base, right? So we have to get in both the same base. Here, right, 125 equals to 5 to the third power. So I'm going to substitute 5 to the 125, right? I'm going to use substitute 5 to the third power for the 125. Now we bring down the exponent equals to 5 to the fifth power. So here we're going to apply the exponential power rule, which means when you have a power, a base raised to a power raised to another power, you multiply the powers. So 3 times x will give us 3x. Now we have the same base, right? We have the base is 5. For both sides of the equal sign. So now we can apply the rule. So then 3x equals to 5. We divide both sides by 3. So x equals to 5 over 3. With this type of problems, you can always check your work. Okay, so I'm going to check them for you guys. So all we do, right, we know that x is equal to 5/3. So we're going to plug it in for the x. Right? You can use a calculator, or you can use the transition from going from exponential to a radical. But here, guys, I just used was a calculator. Okay. So you put 125 to the 5/3 raised to the 5/3 power, but make sure that when you raise it, it's in parentheses because it's a fraction. It's going to give us 3,125, and if you plug in 5 to the fifth power in the calculator, it will give you the same thing, 3,125. So we know this is the correct answer. Solving exponential equations continue. So this one will be 4 to raised to the power of x minus 1 equals 32. If you notice, not the same base, right? Because this is base 4, this is base 32. So let's see if we do 4 squared is equal to 16, right? It's not 32 yet. So let's try 4 to the third power and give us 64. We see, so we know what that means, that we have to find the same base. So 32 must also, 4 and 32 must have a same base, but it cannot be 4. So let's try 2. 4 is equal to 2 squared, and 32 is equal to 2 to the fifth power. You see, so now we got the same base. So I'm going to substitute 2 squared for the 4. We bring down the exponent. I'm going to substitute 2 to the fifth power for 32. Now, on the left side, we're going to use the exponential power rule, or exponent power rule, which means when you have a power to a power, we're going to multiply the powers. So we're going to multiply 2 times parentheses x minus 1. Now we have the same base, right? So now we can apply the rule. So the exponents must equal to each other. So 2 parentheses x minus 1 close parentheses equals to 5. Now we do is distribute. So 2x equals to 2 because 2 times x is 2x, and 2 times negative 1 is negative 2. Now we have to solve for x. We're going to add 2 to both sides. So 2x equals to 7. Now we divide by 2. So x equals to 7 over 2. And again, we can always check our work, so let's check it. We're going to plug in 7 over 2 for x. 7 and 2 minus 1 will give us 5 over 2. 4 to the 5 over 2 power. Now, if we put that in the calculator, guys, it will give us 32. So 32 equals to 32, so I know this is the correct answer. Okay, now, this is called writing exponential equations to logarithmic equations and vice versa. I believe I went over this topic about 2 weeks ago. But anyway, if you have y equals to log of base ax, means a to the y power equals to x. This is on the left is called logarithmic form. On the right is called exponential form. So you have to go back and forth. And this is useful when you're graphing a log function. You have to convert it to exponential form. Okay. But for now, we just essay number 8. Write each logarithmic equation into an exponential equation. Right. So here I have to go from logarithmic to exponential. So here we know that my a is my 9. We know that my is 81. My y is 2. Now we're going to put a to the power of y equals x is going to be what? 9 to the power of 2 equals 81. See, there's my a, there's my y, and there's my x. So this is my solution. Now we're going to go the other way. They're going to give you an exponential. You have to go from exponential to logarithmic equation. So 5 to the third power equals to 125. Okay, so I have to go from exponential to logarithmic. So my a is what? My a is 5. My y is 3. And my x is 125. Right, so my y will be 3 equals to log of base 5 of 125. Or log of base 5 of 125 equals 3. So these are the correct form, either the left or the right. Most of the times in back of the book, right, for the solutions, they have it here like log of base 5 of 125 equals 3. They have it in this form. Okay, but both are correct. Now, how do we graph logarithmic functions? Okay, now in order to graph without a calculator, must convert logarithmic equations to an exponential equation. Okay, y equals to log of base ax, right? We have to go from logarithmic to exponential. A to the y equals x. So for example, we want you to graph y equals to log of base 2 of x. This will be what? 2 to the y equals x. So now we're going to do our table, but instead of plugging in the values for x, we're going to plug them in for y, right? Because y is my exponent. So again, we're going to do like before, right? So when y equals 2, when y equals negative 2, right? So we plug it in there, so it's going to give us 1/4. So when y is negative 2, x is 1/4. You see, here's my solution, guys. And again, repeat the process. Right, when it's negative 1, it's going to give us 1/2. When y is 0, it's going to give us x will be 1. When y is 1, right, 2 to the first power will give us 2. When y is 2, 2 squared will give us 4. See, that's where the 4 comes from. When y is 3, we plug into the x equals to 2 to the third power. It's going to give us 8. And now here's my graph. The one in blue is the exponential graph, and the one in red is my logarithmic graph. These are called inverse of each other, but I believe this the 1324 doesn't cover inverses, but they do it in 1314. Okay, but anyway, the one in red is my graph for the logarithmic, and the one in blue is my graph for the exponential. Okay, now this is going to be a expand or condense logarithmic expression. So for these, there's properties that you have to know. Right, these are properties for the logs and also for the ln's, for the natural log. Property number 1, right? This is called condensed. This is called expanded. The ones on the left are condensed or single log, and the one on the right are called expanded. Same thing with the natural log. These ones on the left are called single or condensed. The ones on the right are called expanded. Okay. So here it says write each expression as some more difference of logarithms with all variables to the first degree. Okay, so for example, on this one here, what what rules are present? Well, I mean, which properties are present? Right, if you notice, we have exponent, so property number 3 here, the exponent, the power property, and also here we're just multiplying, so also the product property. So the product property is present, and also the power property. So for the power property, right, we're going from here to here, right? So we have 1, 2, 3, so we have 3 terms. I mean, we're gonna have 3 terms. We have a 5, x to the 4th, and y cubed. So we need to add 3 separate log terms. Product, right? With product, we add. There's 1, there's 2, and there's 3. So this takes care of the product property. Now we have to take care of the power, the product. Now we have to cover the power property. For the power property, if you notice, right, it should be in this form. You see, there's no exponents. So the exponent goes to the front. Okay. So now, right, exponent goes to the front. The exponent for the log of y, the exponent, the 3, goes to the front. Now that's my answer. Let me go back. So this is my solution here, guys. That's how you write each expression as a sum or difference of logs with variables to the first degree. Now number 12. Again, we have to use the same rules. Write each expression as a sum and or difference of logarithms without variables to the first degree. This is similar to number 11, but here, guys, we have all the 3 rules here, right? This is multiplication, and then we have division, and then we have the power rule. So all 3 power rules are present: the product, the power, and the quotient properties. So here first, right, we're going to apply the quotient, right? The quotient means subtraction. It'll be log of W. Also here, guys, if you notice, there's no base. If there's no base, we know it's base 10, right? So if there's no base, you can keep it with no base, but we know, or we should know it's base 10. And I believe I went over that in the PowerPoint that I covered 2 weeks ago. Okay, now we have to execute the power property. The product property of log of x of y2, right? So these are 2 terms here. We're going to convert log of x times y squared into 2 log terms. There's the first one, plus, right? Product means plus. There's my second one. Now we be down the log of w. Now we have to apply the power. Execute the power, right? The exponent goes to the front. Right? The exponent goes to the front. And this is how we expand it and sum and difference. So we go from the original log of x y squared divided by w. The result will be log of x plus 2 log y minus log of w, and the base is 10. Again, we're going to do another example, but I believe now I'm going to go the other way. Write each expression as a single log term. So in other words, now it's in this form, like expanded, we have to go as a single log. Okay, which properties are present? If we notice, right, it's subtraction. So subtraction means there's going to be the quotient property is present, and if we have a number in the front, also the exponent, the power of the exponent is also present. So power and quotient. So execute the power property. So the 2 goes, the 2, right, that's in the front goes to the top as the exponent. Minus ln of x plus 3. Now, if it's subtraction, right, if it's subtraction, it's going to be division, which would be the quotient, right? So it's going to be the ln of x plus 2, x plus 7 to the second power over x plus 3. Okay, now solving logarithmic functions. To solve logarithmic and exponential equations, need to know previous properties such as, so we need to know these properties here again. Okay, now, what's 6x? 6 to the power of x equals 72. So here, guys, we're going to use the power property here because we want the exponent to come to the front. Okay, so we're going to take the ln of both sides. Okay, we done the exponent, we take the ln of both sides. So I'm going to put the ln of 6 in the front, right, and also in the front of 72. Now, by the third rule here, by the power property, the exponent goes to the front. Now we divide both sides by the ln of 6. Now we use the calculator. So this is my solution, approximately 2.38685280. I believe most of the times they want you to round off to 4 digits or to four decimal places. Okay, that's why those squiggly lines means that this is an approximation because we rounded off. So that's my solution. And we can always also check our work. But this is very important here, guys. The element of a number, it's an actual number, guys. At times, students want to separate. For example, here, they will want to do something like divide both sides by 6. You cannot do that because the ln of 6 or the ln of a number is an actual value. You cannot separate them. Okay? Now let's do number 15. Here's another property. It says let U, V, and A be positive real numbers where they cannot equal to 1. Now here's the condition. If log of base A of U equals to log of base A of V, then U must equal to V. Okay. Now this is number 15. So for this property to take effect, both sides of the equal sign must be as a single log. If you notice, the one on the right is not a single log, so we have to use some of the properties. So this will be the quotient rule, right? So for the quotient rule, right, we're gonna put it as a single log on the right side. So the quotient rule means division. So this will be log of x equals log of x plus 3 over x minus 1. Now we can apply the rule, right? Because now we have the same base and the base is 10. So x must equal to x plus 3 over x minus 1. Now here you can solve this like I think like 2 or 3 different or like 2 ways, right? By the cross product, or else you can multiply everything by x minus 1 to cancel the denominator on the bottom of the expression on the right side. But what I did here, guys, I cross multiplied. So there's an invisible 1 here at the bottom of the x. So you're going to multiply x times x minus 1 must equal to x plus 3 times 1. So we're going to get x times x minus 1 equals to x plus 3. Now I'm going to distribute. So x times x will give us x squared. X times negative 1 will give us negative x. And the x plus 3 on the right side, we'll just bring it down. Now since we have x squared, so we have to let it equal to 0 on the right side. So we're going to subtract minus x and minus 3 on both sides. You see x minus x will give us 0. 3 minus 3 will give us 0 on the right side. On the left side, we have x squared. And we can combine the negative x minus x will give us negative 2x. So it's going to give us x squared minus 2x minus 3 equals 0. Now you have to factor. Okay. This will give us x minus 3 and x plus 1 equals to 0. So we're going to apply we're going to set both binomials equal to 0, or we're going to apply the zero property theorem, which means but we're going to set the x minus 3 equal to 0 and also the x plus 3 equal to 0. That's the zero property theorem. Okay, so now, so for x, so on the left side, we're going to add 3 to both sides, so x equals to 3. And here on the right, we're going to subtract 1 to both sides, so x equals to negative 1. So these are my two solutions. But remember, we must check the work. Now here's what I tell my students. Plug in the log or the ln of a negative number, and it's going to give you something like or undefined, which means the logs, the natural logs cannot be negative. And you also tell them to plug in the log of 0, the ln of 0, and again it's going to give you or undefined, which means that the logs must be more than must be more than 0, not equal to 0, must be more than 0. So in other words, the negative 1 here, guys, will not work because if we plug in negative 1 for the x, it's going to give us an error, right? Not defined or an error. That means that negative 1 is not the answer, not a solution. Now, if we plug in 3, well, we plug in 3 for every x, so we're going to get log of 3 equals to log of 6 minus log of 2. Now you can plug this in the calculator, guys, because they're both base 10, which most calculators they do the operation only on log base 10. And here we can actually do it, guys. If you put that in the calculator, you're going to get right This is the answer on both sides. But if you want, you can do this without a calculator. Let me show you how. So, right, so the left side's okay, but the right side, right, we have the same base, which is base 10. So we're going to condense it and do it as a single log, which means we're going to use the quotient rule or the quotient property, right, which would be the 6 divided by 2. So 6 divided by 2 will give us 3. So the left side and the right side, they both give us log of 3, which means 3 is the correct answer. Okay. So that's a solution. Let's try one more rule here. We have if a and u are positive real numbers with a cannot equal 1, if you have a to the power of log of base a u, that will equal to u because the base a to the power of log of base a, those is equal to 1. So we bring down the u. So in other words, I'm going to do number 16 and we're going to apply the rule here. Okay, for example, I don't want log of base 4. You see, I don't want it there. So I'm going to raise, I'm going to make 4 the base on both sides. You see, so I'm going to make it 4, right? So this will be my base now, but I have to do it to both sides. Now, by applying the rule here on top, how it works, if you have 4, a log of 4, that cancels, that's equal to 1. So we just bring down the 5x plus 6. Right? And then we bring down the right side, we bring down 4 squared. Now 4 squared is equal to 16. Now all we do is solve for x. We subtract 6 to both sides. So 5x equals 10. Now we divide by 5. The answer is 2. And again, you can always check your work. Okay, so we're going to plug in 2 for the x. So log of base 4 of 10 times 2, 5 times 2 is 10. 10 plus 6 is 16. So now, right, so now, if you want, right, so log of base 4 of 16 is equal to 2. So that, but here, guys, let's apply the rule which is called the change of base, which I didn't put it here, guys, because this cannot be put into most calculators. Okay, that's why this, to apply the change of base, it will be log of 16 divided by log of 4, and that will give you the 2. Okay. Now, this is chapter, I think I'm going to do like 4 more problems. Let me see how much time I have. Yeah, I'm okay. So this is 5.1, which was simple interest. Okay, Gabriel invested his summer earnings of $3,000 in a savings account for college. The account pays 1.5% simple interest. What will be the value of the account after 2 years? And how much interest did he earn? Okay, so this is my formula. So I'm going to put everything in, right? So we're looking for the future value because what will be the value of this account after 2 years? So we're looking for FV, which means future value. So the 3,000 has to be the present value. The R is the interest rate. The interest rate is 1.5%, but you have to convert it to a decimal. So you can do it 2 ways. You can move the decimal place 2 places to the left and drop the symbol, or you can divide by 100. Either or will give you the same thing, which would be 0.015. The time has to be in years, right? So this is in years, so it's 2. Now we do is plug into the calculator just the way it is. Right? So after we plug it in, it's going to give us something like 3,090. So for the first part, right, what will be the value of the account after 2 years? So the answer will be 3,090. So how much of that money was interest earned? So for the interest will be the future value minus the present value, or what you got in 2 years minus what you inputted, which was 3,000. So it's going to be 3,090 minus 3,000. So the interest earned was $90. Okay. And the interest earned was $90. This is number 17. Now let's do number 18. Number 18 is also in the past, like for example, this year they updated the book that's being used for this course, and it's the same author, but they did some changes there. Last year, or the previous edition, the simple interest was 5.1, and compound interest was 5.2. But for this new edition, both simple interest and compound interest are in section 5.1. So this is still 5.1. But for here, guys, there's a different formula. Okay. And the future value stands for the future or maturity value. The PV stands for principal or present value. The R stands for the interest rate converted to a decimal. The M stands for compounded periods. The number of compounded periods per year. T is number of years. The I is the interest rate per period, which is R divided by M. And the N is equal to M times T, which is the total number of compounded periods. And these are the key words for compounded. So this is what you look for, right? It says if the word problem has yearly or annually, M is equal to 1. Bi-yearly or semi-annually, M is equal to 2. Quarterly, M is equal to 4. Monthly, M is equal to 12. What's next? Weekly, M will be 52. If it's daily, it's going to be 360 or 365. If it doesn't say to use 360, then you use 365. But if it's specific to use 360 instead of 365, well, you have to follow the instructions of the book. And if it's continuous, it's a different formula. Okay? So let's do an example here. Now, how can we use compound interest? Compound interest can be used to invest a certain amount of money without depositing additional money. It's like, for example, say that you have $10,000 there at your house, but you want to put them in an account that you can earn interest. So this is a type of account that you put it into. All you do is put the money that you have there, put it for some time, and then at the end of that time, you're going to get all your money back plus a little bit that you made in interest. Okay, that's how this works. Let me show you an example. This will be number 18. Okay, now here's a scenario. You deposited $9,000 in an account at your bank that pays 2.5% interest semi-annually. How much money will be in your account after 10 years? And how much interest did you earn? Hey guys, this is actually like a real life, example. Right now, because back when I was growing up in the 70s, 80s, and 70s and 80s, they used to give you a lot of more interest, like 7 or 8 or even 9%. The higher the interest that they give you, or the bank gives you, right, for depositing some money there in their account, is much more if the interest is higher. But right now it's about 2.5 to about 3.5%. So this is more accurate right now at the moment. So then this is my formula, right? So it's better to use this one because it's easier in the calculator. Okay. So again, there's always 7 things that you must get right. So the FV is 1, the P, the R, the M, the M times T, which is the I is equal to R divided by M, and the N is the M times T. So here, guys, right? So we're looking for how much money will be on your account after 10 years. So we're looking for the future value after 10 years, right? That's what we're looking for. So now, after we know what we're looking for, we begin to extract all the info from the word problem. For example, you deposit 9,000, so 9,000 will be the present value. The R is the interest rate, which a key symbol is a percent symbol. That means that's your interest rate. So it'll be 2.5%. But you move the decimal point 2 places to the left, and you drop the symbol. It'll give us 0.025. Now on the previous slide, I gave you all the key words for the M, which means compounded. Here, guys, it says the interest semi-annually, which is 2, so it's going to be 2. The time is 10, right? In 10 years. Now for the I, we divide R, which is 0.025, divided by 2. Will give us 0.0125. And the N is M times T. The M is 2 and the T is 10. So it's going to give us 20. You see now, guys, it's easier to put into the calculator. So you're going to do it just the way it is in one flow. So you put it 9,000 parentheses 1 plus 0.0125 close parentheses to the 20th power. This is what you get. And most of the times, most of the times it's going to say to round out to the nearest penny or round out to the nearest dollar. The nearest penny will be 2 places from the right, from the decimal point, which would be my hundredths place. But you always go to the third place, right, the thousandths place, and if it's 5 or more, you add 1 to the hundredths place. So in this case, it's going to give us 11,538 and 34 cents after 10 years. So that's how much money you got after 10 years. But remember that we only invested 9,000. So we subtract the 9,000 from the future value, which was 11,538.34 minus the 9,000 that was invested. So the answer will be about $2,538.34. This is how you use these type of problems. Okay. Now this is future value of a renewing annuity. Here it says, at the end of each quarter, a 50-year-old woman puts $1,200 in a retirement account that pays 7.2% compounded quarterly. When she reaches 60, what will be the value in the account? And how much interest will she earn? Okay, for this one, it's a different formula now. This is, it used to be 5.3 on the book, but now it's 5.2. So again, there's always 7 things, right? There's 1, 2, 3, 4, 5, 6, 7. So here, guys, let's see what we're looking for. It says here, when she reaches 60, what will be the value in the account? So we're looking for the future value again. So the payments are $1,200. Now the interest rate, right, is 7.2%, which will give us 0.072. Compounded quarterly, so my M will be 4. My time, right? I mean, here, guys, they don't give you the time, right? But they did give you some hints. It says that the lady was 50, right? When she started this account. Now she wants to know how much money would you have when she's 60. So then 60 minus 50 will give us 10. Now the I will be the R divided by M. My R is 0.072 and my M is 4. So that will give us 0.018. The N will be M times T. Well, 4 times 10 will give us 40. So all we do is plug everything in the calculator. Right? Here, guys, all we do is start with a numerator. We're going to plug it into the calculator. And I believe I did something similar last week on the presentation that I did for Math Happy Hour. So you put that in the calculator, guys, it's going to give you 1.041320138. Now you're going to hit the division key, right? Press on the division key. Then this is what you should see when you do that. Then you're going to press 0.018 and enter it, which means you're going to divide the numerator by the denominator. And this is the answer that you should see on your screen. 57.88511,879. Okay. Now we multiply. We're going to hit the multiplication key. Right, and then this is what you should see, that we're going to multiply by 1,200. So this is my answer, guys. It's going to be $69,421.34. So how much of it was interest? Let's see. How many payments did she make? She made 40 payments, right? Or she did 40 deposits. So 40, right, times 1,200 will give us 48,000. This is not bad, guys, right? So like a little bit over 20,000 is what she earned, because this is the future value, right, what she got in those 10 years, and she really only 48,000 came out of her pocket. So the rest is interest earned, which is $21,421.34. Now, number 20. This will be the last one, I believe. Yes. Here, you want to purchase a house that costs $325,000 with a 30-year fixed rate at 3.9%. What are your monthly payments and how much interest that you end up paying? Okay. So again, for this one, it's going to be a different formula again. So this is a formula that we're going to be using. Okay, so we're looking for the payments, right? So the house this formula is called the present value of an annuity. Annuity, because this is the money that you borrow right now at the present value. The bank loaned you this money to buy the house. So that's how much the present value or the money that you borrowed, the amount of money that you borrowed. Now the interest rate is 3.9%, which will give us 0.039, right? And most of the times, right, it's going to be monthly payments, so the M is equal to 12. The time is 30 years. So the I will be R divided by M, 0.039 divided by 12, to give us 0.00325. And the M will give us M times T, which will give us 12 times 30, will give us 360. So you're going to make 360 equal payments. Okay? But how much are the payments? That's what we're going to find out. Okay, now here, guys, I believe I also showed this example last week. To find the payment, right, I'm going to show you one steady flow without leaving the calculator. I mean, without pausing it or without clearing the calculator. We're going to use the inverse key. So first here, we're going to put in the calculator what's in the numerator, right? The 1 minus parentheses 1 plus 0.00325 close parentheses to the power of negative 360. If you plug that in, this is what you should see in the calculator on the screen. 0.6890436901. Now, right, now we're going to hit, because now this is division, so now we're going to hit the division key. This is what you should see. Answer to the right, to the negative to the answer divided by on the screen. Now we're going to enter the 0.00325. After we do that, this is what you should see on your screen. 212.0134431. Now here's where you're going to hit the inverse key. That is the inverse key. So you're going to press on it, and this is what you should see. Answer to the -1 on the screen. Now you're going to enter what's on the left, the 325,000. So this is your monthly payments. This is what you got, which will be $1,532.92. Those are the payments that you'll be making every month. And this is not including the property taxes and also the insurance for the house. Okay, just the payment. Now, so how much money did you end up paying? You see, the house was $325,000, right? That's how much you borrowed from the bank. But in 30 years, let's see how much you end up paying for the house. So there was 360 payments. So 360 times $1,532.92 will give you $551,851.20. That's how much you end up paying for the house, which like 225,000 more or less. Okay, now so how much interest did you pay? So you subtract what you borrowed from the bank minus the total that you end up paying, which was $226,851.20. That's a lot of money that you end up paying extra, right? But there's a way to not pay that much. What you do is you put in extra money every month that you tell the bank that you want it to go straight to the principal. That way you can pay it off quicker. I use mathematics to pay the first house that my wife and I got. We paid it in 10 years, but we used mathematics, and we always gave something extra. So in order to pay off the house, and you can do the same thing, because the banks at first, what they want is their money. So most of the money from the payment that you're paying every month goes for the interest. Okay, so I want to thank you guys for showing up to Friday Math Happy Hour. And if you have any questions, please let me know, so maybe I can answer them for you. Okay, thank you.
Thank you, Mr. Sasi, for your wonderful presentation. We do want to remind you all about your previously recorded sessions, which are available on YouTube playlist. Today's session will also be available on the playlist later today. Also linked is a short survey to help us improve our TVE sessions. So please take time to fill that out before you leave the room. And before you leave, I do want to share the TVE sessions that we will have next week. So for the week of October 20th, Happy Math Hour in room Math 1314. Professors will be going over exponential and logarithmic functions. And for Math 1324, Professor will cover systems of equations. Just a friendly reminder that student success topic for that week will be degree plans with Debbie Santana and Mary Favela. If you guys have any questions, please feel free to use the chat or open up your mics. If not, we hope to see everyone again for Math Happy Hour next week. Have a great day, guys.